Hey everybody, welcome to a brief introduction to R. In this video, I'll be going over the history of the R language. We'll be discussing the features that make R a great language, and we'll dig a bit deeper into the features that really make it stand out. We'll then do a code demo where I'll be solving one of the exercises on the R track, and we'll finish off with listing some of the resources that you can use to learn R. I'm really excited about R, and I hope you will be too after you've watched this video. So let's get started. The R programming language was created by Ross Iyeka and Robert Gentleman at the University of Auckland. R can be considered a re-implementation of the S programming language, which is a statistical programming language that was developed at Bell Labs in the 1970s. The S language itself was succeeded by S+, but S+ was a commercial product, and Ross and Robert felt like they wanted to work with an open system. So they set about building R. As R is a re-implementation of S, a lot of the syntax is very similar to S, but its semantics are different though, as they were inspired by the functional programming language Scheme. The goal was to create a language that was better suited to statistical computing and graphics and easier to use than any of the existing systems, which were designed by computer scientists, not by people well versed in statistical computing. The language is a dynamic and strongly typed language, and it supports multiple paradigms. So there are different ways in which you can program in R. The default way is a functional way, it's a functional core, but you can also do procedural programming or object-oriented programming. R is used in a wide variety of places, from healthcare, where, for example, R is used to analyze preclinical trials of new drugs, but also in finance, in Natural Weather Service, which uses R to help predict weather. John Deere uses R to estimate the number of spare parts that they need to produce. And R is used on universities to help teach data analytics and statistics. So a lot of different places, but basically everywhere where statistical computing is being done, R is being used. Let's go into the reasons why R is a great language. First of all, it's flexible data types. The core data type in R is a vector, and a vector is a collection of elements of the same type. So you can have a vector of integers, a vector of booleans. A matrix is a data type that's a vector, but with multiple dimensions. And you, of course, have a lot of goodness in how you can multiply matrices, etc., because it's key to doing statistical computing. There's also a list data type, which is sort of similar to a vector, but its elements can have different types. And there's also a data frame. And the data frame is really interesting because it is specifically designed to work well to represent research data. So a data frame is a collection of rows and columns, and the rows would be the individual measurements, and the columns would be the things that were being measured. So this is ideal if you want to analyze your research data, which is often in the form of having rows of data with columns of the thing that they are measuring. As I said, the core type is the vector, and a scalar value, which is like a single integer or a single boolean, is also a vector. It's a scalar vector. So there is no such thing as just having an integer by itself. An integer by itself is actually a vector with that integer. And that might seem odd at first, but it's actually incredibly powerful, and it allows you to do a lot of goodness with vectorized operations, which is another thing that R is great at. A vectorized operation is something that can be applied to every element within the vector. So if you have a vector with a couple of integers and you do +2, what you actually get is the 2 being added to every single element of the vector, and that gets returned. And this allows you to very easily work with transformations or filtering of data on vectors, so on a collection of values, without having to write any sort of looping. And these vectorized operations are also very performant because they can be parallelized, etc. So vectorized operations are incredibly cool and powerful, and you should definitely be using them if you are using R. A second reason why R is great is that it has a massive collection of packages available via the Comprehensive R Archive Network, or CRAN. There are almost 20,000 packages available, and they offer a wide variety of things like functionality to use different algorithms to analyze your data, or to add new ways in which you can visualize your data. A lot of goodness in the CRAN. A third great feature of R is that it has easy interop with high-performance languages like C, C++, and Fortran. A lot of very high-performance code has been written in those languages, and if you want to use that functionality, you can easily do that with the way that R handles interop with those languages. So all the goodness that comes from being able to use every bit of software that was written in those languages is at your fingertips when using R. The last feature that is great of R is that it has a great community. It is friendly, diverse. There is a R for Data Science online learning community, which is quite a mouthful, but it is a great way where you can engage with the R community, learn about R, and just ask questions if you have them, and learn R in a very, very friendly way. It's accessible. And there's also an open Slack group where you can keep in touch with other people. So all in all, the community of R is very open, which is also why R was developed in being an open language, and the community has the same goals in mind. Let's go into R's standout features. First of all, R is a fully integrated suite of software facilities for data manipulation, calculation, and visualization. This means that R gives you everything you need to do exploration, visualization, or manipulation of data. The best way that you can do this is by using the dedicated R IDE called RStudio. RStudio has a lot of features that help you work with data, like having an environment, which is an overview of the data that you're currently working with, for which you can easily inspect. There's also a REPL, which allows you to work with code in an interactive way. And there is built-in visualization of plots, etc., all within the IDE. I highly recommend you try out RStudio because it's such a nice way to work with R and data in general. The second standout feature is R's metaprogramming support, which actually shows its scheme influence, which is also a metaprogramming language. And with metaprogramming, you can work with and generate code using code. And one especially useful way in which you can do that is via writing little domain-specific languages, so DSLs. An example being a library that allows you to write normal R code, but it will actually translate the code into SQL statements. So you don't have to work with the actual SQL syntax. You can work with R code, and the DSL and its metaprogramming implementation will convert that to SQL at runtime. So metaprogramming is excellent in R, and you can use it to extend the language without actually having to extend the language. I think it's time we start looking at some actual R code. What I'll be doing is I will be solving the Raindrops exercise on the R track. And Raindrops is an exercise where you take in a number and you have to return a string. And that string is returned according to a number of rules. If the number has 3 as a factor, so it can be evenly divided by 3, you add pling to the result. If it has 5 as a factor, you add plang. And if it has 7 as a factor, you add plong. If, though, the number does not have any of these factors, you return just a string version of the number. And that's the entirety of the exercise. Before we do any actual coding, I want to note that I am using the RStudio IDE to code in, and this is the recommended way in which you work with R code, because it's fully integrated and has a ton of great features that I'll be showing you in this code demo. So let's look at what we get as a starting point. And we start out with the simple, there's a Raindrops identifier, and it's actually assigned to a function. So Raindrops is a function that takes a number. There are no types. This is a dynamic language. And then we need to add our code here. So let's start implementing Raindrops. The algorithm is as follows. We will have a vector, and that vector will contain the sounds, if any. And at the end, we will check if the vector is empty. We'll return a string version of the number. Otherwise, we will concatenate all the elements within the vector into a single string. And to do that, we need a vector. So we'll say sounds and assign it to an empty vector. So empty vector is C with parentheses. And you can also use C to create vectors that are not empty. And we'll see that later on in this demo. But for now, we'll use an empty vector. One thing to note is that we're using the left arrow sign to assign a value. In C-like language, you are probably used to doing an equal sign. That is possible, but it is actually recommended to do the arrow. So we'll just use the arrow for here. Okay, so then what we do? Well, we need to determine whether or not the number is a factor of 3. So and for that, we can actually use the console a little bit. So we'll open the console, and the console is a REPL-like environment. So I can just put code in here. I can see 1 plus 2, see the results. So let's see if we can just explore things a little bit. Well, we have a number. So number, and we'll just put it to some default value of maybe 6. And you can see here, once I did that the right side hand of this page changed. So the environment is a collection of all the values that have been evaluated in the console. So we have defined a number, which means that on the right side, it is now also listed. So if we update this, so we're going to say the number is, I don't know, 15. We see that the value is updated here too. And that's this is a really nice way to explore your data, because you don't have to keep every single value in your head. You can just check the environment. Okay, so we have a number, and we need to determine whether or not 3, 5, and 7 are factors. And to do that, we can use the modulo operator, so which is percentage in R. So we're going to say number percentage of 3. If we run that, it will say 0, and 0 is then the remainder. So if the result is equals to 0, then it is a factor. 3 is a factor of the number. And you can see here true. And it's actually interesting that this is implicating that it's actually a vector of size 1. So I mentioned before that in R, you don't really have scalar values. So true is actually a scalar vector. So it is a vector with one element. And you can see that by, if we do this, so we're going to say, check if true is equal to the vector with the single true value. And this is actually true. So same goes for numbers. 3 is equal to the vector of 3. And just to be clear, this isn't the same thing. So you can work with things as if they were regular scalars. So you can just use 3. You don't have to do combine 3. But do keep in mind that they are actually vectors under the hood. So, well, then the second thing we can now detect how to, if it's a vector, is how do we append things to the vector. So I happen to know that there is a thing called append, and we can actually look at its documentation. So we can do question mark append, and you saw that I got code completion there. If I run this, it will open the help section on the right side. And the help section contains the documentation for that function. So the console and the right-hand side, the help and the environment are all linked. And this is incredibly powerful if you want to have a quick exploration of the functions that you can use. So what's really, really cool is that there is often a run examples section where you have, for example, this code being executed, and then you get this result. So we don't need to get into the specifics there, but it's good to know that you have ways. You can also search for, I could also have searched for append. That will be fine too. But if you know the function and you want a quick refresher, you can do a question mark and then the function name. So for example, question mark C would give us the documentation for the combine function. So all very helpful, and I think we now have enough information to actually start implementing things a bit. Let's clean up our things a little bit. I'm going to close the console. I'm going to do that right here. So let's use the logic that we previously discussed. So we're going to do if number percentage 3 is 0, which means that, hey, the sound is a factor, 3 is a factor of the number. Then we're going to say append sounds, comma, pling. And the append function will return a new value. So this won't actually modify sounds. So we have to reassign sounds. So we could actually run this code too. So if I run this via console enter, it will send it to the console. And then we have sounds here. If I skip, I could also do this. We have number in our environment with the value of 15. So I'm going to run this and you can see that sounds is now changing to pling. So very nice way of exploring this data. I'm going to copy this. I'm going to say number is 5, then it's plang. Number is 7, then it's plong. I'm going to close the terminal a bit for some real estate. And then we need to add, let's just assume the happy path for now. So where there is a vector, at least one. And then we need to combine it, the vector into a single string. So we can do return. And then there's a paste function. And the paste function takes in a vector. So in this case, that's sound. And we have to specify how we want to combine the strings. So in our case, we just want to append them without any additional strings. So we're just using the empty string. So let's see if this actually gets us to have some tests be passing. And we do. We have 3 failing tests, which is to be expected because we haven't implemented the full spec. So let's do that. So the thing that we need to check is if there aren't any factors. So if the length of the sounds vector is equal to 0, then we return, well, we need to return the string version of the number, and we include it via as.character. And you can see I got nice code completion here. So we're going to say as.character number, rerun the test, and we should now get everything passing. And we do, so that's great. One tiny thing that we can do here to refactor is we don't need this return. By default, the last expression will be returned. So this should be the same thing. And we do. So we now have a working version of Raindrops using a fairly imperative-like approach. And but there is a different way in which you can do things. And let's try a different approach. For our second approach, we're going to use vectors, but in a completely different way. I'm even going to get rid of everything that's here. And I'm going to change sounds to be pling, plang, plong. Then we'll have a second vector that's called factors. And factors has 3 values, so the corresponding factors, 3, 5, and 7. And then to best illustrate what we're going to do, I'm going to send this to the console. I'm going to make the console a little bit bigger because that will help us explain things. And at this point, it's important to know that most operators are vectorized. So if you remember, we did number percentage 3, and we got back a vector with 1 value. So this looks like it's a single value, but it's actually a vector. And you might remember that every scalar value is actually a vector. So this is actually the same thing as doing this. So applying percentage to the vector with just the single 3. If we apply it to 3, 5, and 7, we get a very interesting result because we get back a vector with 3 values. So this is what's called a vectorized operation. The operation is applied to all the elements in the vector. So we can do number percentage factors, which is the same thing, but reads a bit nicer. And we get back a new vector with 3 values, 0, 0, and 1, which is the result of applying percentage to each of the individual values within that vector. We can then chain this. So we're going to say equals to 0. And then we're going to apply equals 0 to every element in the previous result. So this will give us true, true, false. And now things become really interesting because vectors in R have a thing that's called subsetting. And with subsetting, you can select a certain number of values from a vector. So one way in which you can do it is you can do indexing by index. So in R, elements start at index 1. So this gives us the first element, second, etc. You might remember that this is actually the same thing. So vector of 2, but you can also do 2, 1. So we give us the second element and then the first. You can repeat values, and that's all great. But in our case, we need something different because we have values that are Booleans that are corresponding to the corresponding index in the other vector. So this is the first value, second value, and don't return the third value. Well, you can do that in R. So you can say true, true, false will give us elements 1 and 2. So pling and plang. If we do true, false, false, we just get the first element. So as a matter of fact, we can use this to have this result as the subsetting of sounds. So this will give us the first and the second element because the result of this was true, true, false. And this is precisely what we need in our code. So we've now used vectorized operations to convert the number and the factors to first integers and then to Booleans. And then we're going to use those Booleans to select the appropriate elements from the sounds array, a vector. So we're going to say rain is equal to sounds. And what we could also do is we could just immediately convert this to a string. So whereas we did that previously at the end, we're going to do this immediately. And then we can do if the length of the characters is equal to length of rain is equal to 0, we're going to return asp.character number. Otherwise, we're going to return the string, and this should still pass all the tests, hopefully. And it does, so good for that. Then if we go back, we can actually do something differently. This is, of course, a very common pattern where you have one value for an if statement to return otherwise a different thing. So we can just use the if-else function. Then we're going to say, this is the condition. If the number of characters is greater than 0, then what we need to return is the string. Otherwise, we're going to return the number as a string. So slightly shorter. Run it. Still passes the test. I'm going to close that one. We could even be explicit and say this is the yes case and this is the no case, which I quite like actually. So let's do this. But this is the same thing. This is just giving names to the arguments. But the key thing that we now have done is that we used subsetting and vectorized operation to greatly shorten the code while still being very readable. One thing that I don't like about this approach is that we have the sounds and the factors as separate vectors, so they're not linked, but we can actually link them. And we can do that by using the fact that vectors can have names. So values in a vector can have their own names. And this is somewhat similar to having a dictionary or a map in another language. And it works like this. So instead of having this vector with pling, we're going to say pling is 3, pling is 5, and plong is 7. So we're now assigning names to the values. The value of this this vector are still 3, 5, and 7, but they now have names. So let's send this to the terminal. And if we then see what's in sounds, we can see that it's actually displayed in a table format with 3 having the column value pling, plang, and plong. So that's all great. The second step that we can do is we need to see if this still works with our vectorized operation. So we're going to do sounds number percentage sounds equals 0, and we still get back the true, true, false values, and we get back the names, and that's the thing that we are interested in. So you just in case this is not clear, so percentage sounds is the same as the values of the vector. So this is 3, 5, and 7. So the names are not actually used there, but we still want the names. So what we're going to do is, this is a true, true, false vector, and we know we can use it with subsetting. So we're going to do sounds and then subset it with this. So we get back a named vector with only the matching elements, and then we can get the names from that. So do this, paste this in here, and then we get our actual values. So instead of doing this, I'm gonna change this bit to this. So now we have the names of the numbers, and this should all still work, hopefully. Run the tests. Oh, it does, but it doesn't, because I made a copy paste file mistake. Yeah, I changed something somewhere, so I'm gonna rerun it. Now everything's passing again. So this is now using named vectors, and I quite like this. There is another refactoring that we can use, and that is that R has an operator that's called the pipeline operator. And with the pipeline operator, you can, instead of having this this nesting of the functions, we can rewrite it. So I'm gonna copy this. I'm gonna comment this out, and this will be a different way of writing this. So where instead of, we will use function calls with parentheses, we're gonna do this. I'm gonna pipe it to the next result. So I'm gonna remove this, and this means that the thing that comes before the pipe is passed in as the first argument of the next function call. So that's actually the same as doing this. And we can apply that same logic here too. So this is the only argument. So we're gonna say, I'm gonna go pipe that into names, and then I'm gonna put this on a single line. So this call is exactly the same thing that we do have here. So I'm gonna remove this. But to me, this reads slightly better because you don't have the parentheses, and it somehow gives you a better visualization of that this is actually like a pipeline of transformations, where transformations are applied repeatedly. So I'm going to run everything, and this still all passes. And I think we're now at a point where I'm quite happy with the solution. It is nice and short. We use named vectors, we use subsetting, so we use a lot of what makes R great, and we get a nice and concise solution to Raindrops. The final thing that I'd like to show you is how easy it is to visualize data from within RStudio. What I'll be doing is, instead of having this single Raindrops function, I'm gonna add all three different versions. So there's the if version, the vectorized version, and the named vector version. And then there's this bit of code that runs benchmarks. So it will run these inputs on all those functions. And then does this for 1,000 iterations. So these are all packages that I pre-installed. So let's run the benchmark first. Okay, that's finished quite quickly. And then what we can do is we can plot these results. So I'm gonna reshuffle things a little bit so that we have a nice big plot window. I'm gonna run this, and it will generate a plot version of the benchmark results. Obviously this is incredibly useful right now, but we can see here that for n=1, that the if version is faster than the other ones. It doesn't exactly show off that vectorized operations can be really fast, but that's because we have very tiny vectors. So if you have large vectors, the results will be completely different. But this is a nice way to demonstrate that it is very easy to plot. So running the benchmark was easy, but plotting it was probably just as easy because it's just a single line. And you get this nice integration in RStudio. The plot is visualized, and this is a great way when working with data. Let's look at some resources that you can use to learn R. First of all, you can learn R by doing the R track on Exercism. It has over 35 exercises that have you deal with a wide variety of topics, from working with strings to integers to matrices, and I would highly recommend you using Exercism to try out R. If you've solved an exercise, I would also recommend you looking at the community solutions. And the community solutions are submitted solutions by other users that have solved the same exercise. And as R is a fairly unique language, there are often ways in which you can solve the exercise that you might not have thought of. So I would highly recommend you looking at the community solutions to see if there are different ways and interesting ways, or maybe even very elegant ways in which you can solve the exercise that you might not have thought of yourself. A second resource that you can use is the R language definition. And this is the official definition of the language. So it contains basically everything that's in the language, from vectors to lists, and it's a great reference. Then there are the R manuals. These are also all official, and they have different topics like an introduction to R, but also how to write extensions, or how to do data import and export, how to install the language, etc. So a lot of nice stuff here. There's also the online ebook, Hands-on Programming with R. It's also an actual book, but on this website, you can read the entire book for free, and it has you working with R in a very, well, it's a hands-on approach where you're actually building something. So for example, there's a project where you're building a slot machine, or where you're playing cards. And this very practical approach to learning R works excellent. So I would highly recommend you trying out this ebook. Another book that's great, and that's completely viewable online, is the Advanced R book by Hadley Wickham. It contains a listing of basically most of the higher level topics, like how to do functional programming, how to do stuff like classes, etc. But also it contains things like vectors and subsetting, which we've mentioned in the code demo. This is an excellent book. It's well written, and I highly recommend you trying this out. The same author has paired with Garrett Grollman to write R for data science. So if you are interested in R, but you want to use it for data science specifically, this has you covered. So everything from importing data to tidying up your data and visualizing, everything is covered in this ebook. So highly recommend you trying this out if you want to use R for data science. There's also a free Getting Started with R course that you can use, which is also excellent. There's a video series, Writing Scripts of Code in R, that has someone going over writing scripts in RStudio and showing how to do that. And then finally, I've mentioned this before as one of the strengths, is there is an R for Data Science online learning community. And you can go here, and there's a reference to the Slack, and there's a lot of goodness. There are a possibility of maybe being mentored by an R mentor, etc. So if you want to engage in the community, this is the place where you need to go. And with that, we've reached the end of this video. I hope this introduction video was useful to you, and that you're now keen on trying out some R yourself. R is a very unique language, and I highly recommend you trying out R via the R track on Exercism. Hope to see you soon. Bye.